Civil engineering is a major to consider if you want to design bridges, dams, roads, tunnels, buildings, railroads, pipelines, and even some civil engineers will work on aircraft or spacecraft structures and more. But depending on what projects you want to work on and what aspect of those projects you want to work on, you will go into certain subfields which can lead to very different career paths. The main subfields I will talk about that you can dive into in college are structural engineering, geotechnical, water resources, and transportation. All civil engineers will take mostly the same classes their first few years and learn the very basics of all of these subdisciplines. Then maybe their third, but especially their last year, they will take a lot of electives in the field or maybe fields they want to focus on. So first, structural engineering is about calculating and understanding the forces, strength, stability, and so on within a structure. It could be a bridge, a skyscraper, a landmark, or even a spacecraft or aircraft. Remember, these structures are very heavy and need to support their own weight so that they don't collapse. Now this subfield is the most math intensive and has lots of physics. All civil engineers will take a class called statics, which is all about the forces and systems that are not moving. In basic physics, you may have done a statics problem, like where does this support have to be for the system to be totally balanced and therefore not moving. You summed all the forces which equaled 0 and all the torques which equaled 0. And that's the basics of statics. So if you're looking at the forces within a bridge or truss, well, the same principles apply, but now there's just more to it. The weight is straight down as shown in blue, all the beams exert forces on one another, but the sum of them is equal to 0, and the torque sum to 0 as well because the bridge is not moving. And it's of course even more complicated than this, but if you enjoy that kind of basic physics you see above, then you'll likely enjoy the statics and physics you see in structural engineering. So that's just a very simplified explanation, but now let's dive into some of the classes they would take. One class that would be important for structural students is a reinforced concrete class. In concrete structures, they reinforce it by putting steel beams in the concrete. We can't see those beams, but here, before construction is done, you can see them sticking out. Or you can see a lot of them on these unfinished columns. So why do they do this? Why isn't concrete good enough? Well, concrete alone, once hardened, has low tensile strength, as in it does not handle being pulled very well. However, it's okay with being compressed. But to counteract that low tensile strength, they add steel beams and pour wet concrete, which hardens around them, and then those steel beams have high tensile strength to counteract those types of forces on the structure. So in a lab for this class, you might build the rebar, or the steel reinforcing rods, pour the wet concrete onto them, then once it dries, use a machine that holds the beam on both sides, then apply forces in the middle and keep increasing the force until the beam breaks or cracks and starts falling apart. That force being applied is sent to a computer that tells us the loading on the beam so we can collect the data and get the properties that we need. You could take structural dynamics as an elective class. Dynamics is about moving systems, unlike statics. So this is one of the few classes where motion is included. So whether it's wind or an earthquake that shakes a building, you need to know how that motion will impact the structure itself and all the forces within it. I've shown this animation before, but mostly for mechanical engineers as it's a vibrating system that they can analyze, but civil engineers could get into this as well. They have to make sure their designs can stand up against any type of movement the structure may be subject to. You could take an elective class on seismic analysis, which is specifically about calculating the responses of a structure to an earthquake, or one on bridge engineering, which would be a class on highway bridges, materials used, distribution of loads and how forces are spread throughout the structure, and so on. Mechanics of materials, like how twisting and bending a beam or column causes it to become internally stressed. Timber structure design, which is about analyzing properties and forces within wooden structures, and much more. See how even if you choose structural engineering, you could still take many different classes from the other structure students? It's a very broad major, but hopefully you really get the idea by now. Lots of physics in this discipline, but mostly statics or forces and structures without movement. In the real world, these engineers often work on the computer and use software for their designs, where that software does that advanced math to determine the forces throughout the structure, like you see here with an office block and its components. You may still have to do hand calculations, but most of the rigorous analysis you learned in school will be left to the software. Now let's move on to geotechnical engineering, and you'll already see how different these disciplines are. Geotechnical engineers are concerned with the behavior of earth materials like rock and soil, but the main focus is soil. This may seem odd, but you'll see how important this is. The structural engineer can do everything right to make sure the building will stand up, but if the geotechnical engineer messes up and you put a structure on soil that can't withstand it or is uneven, the building could fall, sink into the ground, or even lean to one side, probably the most famous being the Leaning Tower of Pisa, which was a result of soil issues. Then they also have to consider the foundation of the structures that are being designed, like should they have a shallow foundation or a deep foundation. You may not realize it, but our houses and all the buildings you see have foundations that go underneath the earth to keep the structure as stable as possible by transferring the weight from the structure to the earth. But geotechnical engineers rely heavily on testing. So a lab you might see in college is to go out as a class and collect soil samples around your university and bring them to lab. You would have to classify it, like is it sand, gravel, clay, etc. There are many soil types, and you may have to look at the grain size or how it reacts to water. You determine its water content by analyzing the sample, which will be comprised of a solid soil, water, and air of different masses and volumes. But most importantly, you'll measure how the soil will react to mechanical loading or to different forces acting on it. So you might perform a triaxial test, for example. Too complicated to explain for this video, but essentially you put the soil in an enclosed area and apply a force or load to the top which pushes down on the soil. Then pressure sensors measure the pressure at different points to see how the soil is being affected. If you imagine a square sample of soil and you add a force to the top, the soil can fail along some weak plane. Basically, the weight overpowers the friction holding the soil particles together, and the soil will start to slide, which is known as shear failure. Its ability to stand up to this is known as shear strength, which is one thing that the triaxial test on the left tests for. And this leads us to what a career in geotechnical engineering could be like. You might be the person who goes out to the field where a structure is going to be built and collects soil samples all around the area for testing. Or you could do testing at the field. One of the most used tests right now in this field is cone penetration testing, where a large truck goes out to the field which has all this equipment on it, and a cone is pushed into the soil, and the pressure will be monitored by a computer on the truck as it moves through the soil into the earth. Based on the pressure, you can analyze the soil mechanical properties. Or maybe you could work in a lab where you would do the testing on the soil after it's been collected, like I showed with the triaxial test. Or maybe you could work on the computer and input the different types of soil from the various locations at the site, so you can digitally lay out the area that the structure will rest on. So you could be in the field, in the lab, or on the computer. Your elective classes could include geotechnical earthquake engineering, which would be like learning the dynamic behavior of soil as opposed to the structure itself. Then slope stability analysis and how to safely design structures on slopes. An example would be an embankment dam. Analysis of deep foundations, where the structure goes deep into the earth for a stronger support, like for skyscrapers. And of course, there are many more classes. Now let's move on to water resources engineering. This is about the design of systems to manage human water resources. They could work on a water treatment facility, designing dams, pipelines, channels, canals, and so on. Maybe you have to design a storm drain system in the event of a large storm. Where is all the water going to go, and how will you get it to the ocean efficiently? Or you could design a canal, which is an artificial waterway to transport water for irrigation, or it can be used for ships and boats. Or you could design a culvert that will allow water to flow under a road or trail or some other obstruction. Elective classes you could take include coastal hydraulics, where you learn about ocean wave propagation, submerged pipelines, seawalls to protect human habitation, and so on. Or open channel hydraulics, which is about fluid flow in an open channel as opposed to a closed channel or pipeline. And last is transportation engineering. This is about safe and efficient movement of goods and people. These are the engineers who design streets, roads, highways, railroads, public transportation systems, and even airports. So maybe this engineer has to look at the kind of demand from a new development, whether it's a new stadium in your city, all the way to a new grocery store in a new location. This is going to cause new types of traffic throughout the area. The engineers would try to optimize how the new development impacts existing traffic. They would look at data from other similar places to see what kind of traffic they get, then try to make improvements where possible. It could be simple, like adding a bus stop in the nearby area, all the way to expanding the roadway to allow for more traffic. They could work on the geometrics of the roadway, such as what radius of curvature does an off-ramp have to be for a car going 55 miles per hour so the tires won't slip. Or if they're going up an incline, the driver needs to see far enough ahead of them to stop if there's a sudden obstacle. Or what do the cross sections of a freeway need to be for the lanes and the shoulders to accommodate the amount of traffic that's expected? Or let's say a highway interchange is being designed. A structural engineer would make it stable and design the structure itself, but the transportation engineer would determine maybe how many lanes are needed for the interchange based on traffic, or how the merging should happen to maximize safety. They make sure that the layout is designed to maximize traffic flow and safety rather than the physics of the structure itself. Often these engineers evaluate potential improvements to cities in terms of transportation rather than create a totally new design. As in, you probably haven't had many new highways put into your city in the last few years, but there's probably been plenty of construction, whether it be adding an express lane or a bike lane, etc. So they might not create a new bus transportation system, but they may optimize the existing one. Maybe they take data from how many people get on the bus, how long the bus takes to complete its route, how long people are waiting for the bus, and so on to optimize the route, the amount of stops, and more. Your career will also likely involve a good amount of computer work. You might have to create a layout of the new lane, off-ramp, bridge, or whatever you're designing on AutoCAD, which is a very important software for civil engineers. Or you could use software to analyze and simulate traffic. You could actually lay out the roadway of a city and use collected data of traffic during different times of the day and simulate new additions. Like you could add in a stoplight somewhere and see what the new traffic would be like. Or you can make a minor change, like make a certain stoplight stay green for just a few seconds longer and see how it affects traffic on those streets. And just note, this is not a very math-heavy field. In fact, it's probably the least math-intensive of the 4 subdisciplines I've talked about. It's more about taking data and analyzing it. Even when I talked about the radius of curvature and how fast someone should be going, you won't use the coefficient of friction and do circular motion physics or anything like that. You use even simpler equations to get what you need. Now that's all the main subdisciplines of this major, but there are some final thoughts I want to include. If you're watching all this and are more interested in the artistic aspect of building and structure designs, then architecture will be better for you. Architects deal more with the floor plans, spatial concerns, and the shape and design of the buildings. They have to have an understanding of structures and physics, but not quite as much as a structural engineer. They would hand off their design to the structural engineer, who would really make sure the entire structure could support itself, and they would deal with more of the technical work. Then, if you want to be the one who puts on the hard hat and does all the hands-on work with the machines and physically builds the structures, then construction will be better for you. But then there's also construction management, which you can still get a job in as a civil engineer. Construction companies will hire civil engineers because of their technical background. Construction is the hands-on part, but construction management is more about guiding the construction, putting together schedules, budgeting, and figuring out how all the pieces will come together. And according to the Bureau of Labor Statistics, the average salary and the number of jobs in the United States for these 3 majors are all pretty good. Of course, these are just averages as of now, but hopefully this gives you a good idea of what you can expect. So if you guys like this video, don't forget to like and subscribe, and I'll see you all next time.